Hi again. I had to take a 45-minute break after I showered. Like, I'm exhausted. But I got some work done during class. It was during class. That's the best I could do. I'm going to be out again this week. Remember, you have in class tomorrow on Tuesday with one of our TAs, Carla. She is fantastic. She's had her own classroom. She teaches. She just came back for her PhD. She will either lecture 8.1 or if you ask her a whole bunch of questions, she'll just answer your questions that day instead. So use the time as needed. Ask her questions. She has access to WebAssign, so she has access to the problems and the solutions. So use her. Use her for sure. Ask questions and see what's up. I will see you next Monday. Next Monday is not a scheduled class day. It's review week. But I think that being gone for 2 weeks and having spring break in there, I'm going to show up anyway. If any of you show up, I'll answer questions. If you don't show up, at least I'm back on campus. All right, no complaints. Now, the math. This section, we're looking at partial fraction decomposition, my favorite section for the entire semester, and I'm bummed that I missed it. But here we go. Well, let's turn that off so I don't accidentally do something here. So section 7.4, partial fractions, what we're going to do is we will learn how to write a rational expression as the sum of two or more simpler rational expressions. Lame example, but we could rewrite 1/6 as a half minus a third. So if you need a sixth of something for a recipe, measure out a half, and then from that half, put the stuff into a third cup. Whatever's left in the half cup will be a sixth. Okay, weird, but still. We're going to do that for polynomial rational expressions. All right. And each fraction on the right-hand side of the equation is called a partial fraction. And together, they make up the partial fraction decomposition. All right, here's a partial fraction. Here's a partial fraction that make up this rational expression. Together, it's the decomposition. We're going to have 5 steps, 6, I guess, every single time. And these are not your steps necessarily. All right, these are going to help us only with step 3. Well, step 1, and then the rest of them are all about step 3. So we're going to divide if an improper fraction. If we have the numerator divided by the denominator, and the degree of the numerator is larger, then we have to divide, find our quotient, and then we'll do the partial fraction decomposition on the fraction that remains, all right, the rational expression that remains. Everything goes forward from there, but we have to check, is it a proper fraction first? All right, is the numerator bigger than the denominator or not? We will then factor the denominator and completely factor it into linear factors and irreducible quadratics. Irreducible quadratics are if we were to solve for x, we would end up with complex numbers. All right, so it's things that do not factor over the reals are irreducible quadratics. For each linear factor, we will have a partial fraction constant over px plus q as many times as that linear factor appears. We'll see this in a minute. And for the irreducible quadratics, we will have a linear numerator, bx plus c, over the quadratic. Notice a constant over a linear function over a quadratic, always 1 degree less in the numerator, always a proper fraction. All right, but that is nowhere near complete for how we do partial fraction decomposition. This just kind of gets us set up. I'll be referencing 3 and 4 as we get further down, probably into the 6th example or so. Let's look at this first one. I'm going to give you the whole thing as we talk about it. Write the partial fraction decomposition of x plus 7 over x squared minus x minus 6. First of all, it is a proper fraction because the numerator is linear, the denominator is quadratic, power of 2 larger than power of 1, it's all good. So I take this denominator, x squared minus x minus 6, and I factor it. You could solve for 0, find your zeros, and then go back and turn them into factors if you're not a factor wizard. That happens. Once we have the denominator factored, I'm going to write the form. And the form is what we talked about in this little blue box up here. These are linear factors. So this rational expression given to us, x plus 7 over x minus 3 times x plus 2, is equal to a constant over the x minus 3 plus another constant over the x plus 2. X minus 3 happens once, so we'll have one fraction. X plus 2 happens once, so we'll have one fraction. A generic constant, we're going to find this a value, and we're going to find this b value. All right. Now, oh, this is going to be hard. I'm using a mouse. Let's see if this works for me. I'm going to use a light gray. Over here, if I were to multiply x minus 3, I'm using the mouse instead of a pen, so it looks like a third grader. X plus 2. All right, I'm going to multiply this times everything, this entire equation. And when I do, notice the x minus 3 and the x plus 2 cancel for this fraction, so I'll just have the x plus 7. When I multiply x minus 3 times x plus 2 times the a term, just this fraction, the x minus 3 cancels out, and I'll have a times x plus 2. When I multiply this denominator by this third fraction, b over x plus 2, the x plus 2 will cancel out, and I'm left with b times x minus 3. Notice how when you multiply by the common denominator, a gets multiplied by the denominator of b, and b gets multiplied by the denominator of a. All right, so this one cancels out. We multiply by what I call what's missing. So if x plus 7 is equal to a times x plus 2 plus b times x minus 3, it's true for all x. So in particular, if x is negative 2, put negative 2 in for x. Negative 2 plus 7, a times negative 2 plus 2, plus b times negative 2 minus 3. Negative 2 plus 7 is 5. Negative 2 plus 2 is 0. 0 times a is 0. Negative 2 minus 3 is negative 5 times b is negative 5b. If 5 is equal to negative 5b, b has to be negative 1. I'm writing downhill here. It really bothers me. I have a handwriting analysis book and I just can't forget about it now. Yeah, anyway, I'll explain why the downward later. Excuse me. Also, for all x, so why not let x be 3? Notice these two values I chose are the exact values that make our factors equal to 0. We can't use them over here. They're definitely not a part of this equation, but they're a part of this equation. So if x is equal to 3, 3 plus 7, a times 3 plus 2, and b times 3 minus 3. 3 minus 3 is 0, so the b cancels out. 10 equals 5a, so a equals 2. Here's my form. I know that a is 2. I know that b is negative 1. I threw the negative out in front and put the 1 on top. You could absolutely write plus and then have a negative 1 up here. That would be completely fine. So what we've done is we've taken this rational expression, which doesn't look that hard, but you know, whatever, and we've made it into two simpler rational expressions. And when you take calculus with me next semester at 1:30, I'm teaching it at 1:30, you will absolutely need this in November. We'll be using this. All right, so that's what we do every time. Is it a proper fraction? Factor the denominator, write the form, multiply, and then we'll have a step 5. This step 5 works a lot of the time. It doesn't work every time though. This is like factoring. Like you have to know what to pick. And it's fairly easy to figure out what it is that I chose. And it's because it makes those 0. That's why I chose them, right? I was able to cancel out the b, cancel out the a. But this, you have to be very careful in how you choose them. So in all of the other examples, I've used a different method. I wanted you to see this one, and you can use this one always, but I like this other method better. And so let's look at example B. If I take x minus 2 over x squared plus 4x plus 3, I see that it is a proper fraction. The denominator has a larger degree than the numerator. I can factor x squared plus 4x plus 3 into x plus 3 times x plus 1. Both linear factors, fantastic. So my form will be my given fraction, given rational expression, is a over x plus 3 plus b over x plus 1. Now a small note. What if you factored it as x plus 1 times x plus 3? Well, when you get an answer for a, that's what I'm going to get for b. When you get an answer for b, that's what I'm going to get for a. We'll end up with the same answer in the end. It just might look different in the middle, right? Depending on your order. I chose this order. It doesn't matter which order. So it's all good. Now notice when I multiply this entire equation by that common denominator, on the left, the whole denominator cancels out, and I'll have x minus 2. On the right, the x plus 3 will cancel out, so I'll have a times x plus 1. And b over x plus 1, the x plus 1 will cancel out, so I'll have b times x plus 3. Now, still in step 4, I would do this particular step. We could use x equals -1 and x equals -3 and find our coefficients like we did up here in blue. But I'm going to show you the other method. The other method is expand this side. A times x, a times 1, b times x, b times 3. So we'll have x minus 2 equals ax plus a plus bx plus 3b. Now check it out. Gather everything with an x. On the left, we have 1x. On the right, we'll have ax and bx. So that's a plus b. We have the x out here, kind of like we factored out the x. We're looking at coefficients. It's called equating coefficients. And the constant terms, I have a -2 on the left. No x with this a, no x with 3b, so we'll have -2 equals a plus 3b. Now this is a system of equations. And we just spent 3 sections of chapter 7 learning how to solve systems of equations. So I'm going to multiply -1 times this top equation, add it to the second equation. I'll have -3, a's cancel out. A -b and a 3b makes a 2b. Divide by 2 and I find that b is -3/2. If b is -3/2, using my top equation, 1 equals a plus a -3/2. I find that a is 5/2. Fractions, very, very common. Notice that 5/2, the 3 over 2, it's a fraction. So this a, I could write 5/2 over x plus 3, but just trust me when I tell you, Webassign wants you to go ahead and put that 2 in the denominator. I already have a fraction here. Let that, a is 5/2, let that be 5 over 2 times x plus 3. A -3/2, I'll put minus 3 over 2 x plus 1. X plus 1's in the denominator, 2's in the denominator, and so on. Every single time. Same 6 steps. Is it proper? Proper fraction. Factor it. Write the form. Multiply. System of equations. Answer. All right, we'll come back to this answer. I ran out of space on this one. So we're going to write the partial fraction decomposition of x to the 4th plus 2x cubed plus 6x squared plus 20x plus 6 over x cubed plus 2x squared plus x. And like some of you might have just, a little gulp. It's all good. Notice though that this is an improper fraction. X to the 4th, 4 is bigger than 3, so we divide. Long division of polynomials we talked about in chapter 2, feels like. What do I multiply x cubed by to get x to the 4th? That'll be an x. So when I do multiply it, I'll end up with 5x squared plus 20x plus 6. Is there anything I can multiply x cubed by to get x squared? No, it's smaller. So this quotient plus this remainder is written up here. So this is now our rational expression. Our rational expression is the quotient x plus our remainder over the divisor. We're going to focus on the fractional part for now. Notice this x absolutely is part of our answer, though. Don't forget that quotient goes up as part of our answer. Let's focus on this part. So I'll take that same denominator, x cubed plus 2x squared plus x. I'll factor out an x. And then I see I have a repeated root. X squared plus 2x plus 1 is x plus 1 times x plus 1. Okay. When we have a repeated root, this is when we go back up to, I think it was principle 3 in the blue box at the very beginning. Our fraction, 5x squared plus 20x plus 6, over the denominator, x times x plus 1 squared. Here's a linear factor, x, so we'll have a over x. X happens one time. Here's a linear factor, x plus 1, so we'll have b over x plus 1. But notice it happens twice, so we have to have x plus 1, and we have to have a denominator of x plus 1 squared. Each of them with a different constant because all three of these are linear factors that lead up to our denominator. So x only occurs once, I'll only write it once. X plus 1 occurs twice in the factorization, so I'll have it at the first power, and I'll have it in the second power as I find my partial fraction decomposition. All right. Then we're going to multiply by that common denominator. Notice, from this denominator, a over x, x cancels out, I'll have a times x plus 1 squared. B has an x plus 1, so one of these will cancel out, and I'll multiply b times x and a single x plus 1. Notice C has the x plus 1 all squared in the denominator, so it's only missing the x, so I'll multiply by x. All right, cancel out the common factors. You end up multiplying the numerator by what's missing from its own denominator. Now we happen to know that x plus 1 all squared is x squared plus 2x plus 1 because it was right here. No sense in redoing your work. Distribute bx times x, bx times 1. Distribute a times x squared, a times 2x, and a times 1. So once we have it all multiplied out, we can equate coefficients. And a time like this is never some time you want to pick. You can pick 0, you can pick -1. It won't be super helpful though, because -1 will cancel out 2 of these. So we won't get our information about b. B might be hard to find. If we equate coefficients though, notice the x squareds. I have 5 of them on the left. I have an ax squared and a bx squared. So 5 equals a plus b. Just the coefficients. These are only x squareds. Now if I look at the x terms, I'll have 20 on the left. Just x, I have 2a plus b plus c. Constant terms, I have a 6 on the left. No x's is only this term a. So we know a equals 6. If a equals 6, I can find 5 equals a plus b. 5 equals 6 plus b, so b must be -1. If a is 6, 2 times 6 is 12. -1 is 11. 11 plus c equals 20, so c must be 9. Oh, I was trying to figure out how that answer rectified itself. It doesn't, because we're going to keep it in blue right up here. A is 6. A is over x, so 6 is over x. I have b is a -1. B is over x plus 1, so that's -1 over x plus 1. C is 9, so 9 over x plus 1 all squared. The quotient and the partial fraction decomposition all together in the answer. And b is going to be the same way, so we're going to have to divide b as well. We have an improper fraction. Yeah, I'm going to keep rolling. You guys hit pause if you need to while you're writing. Make sure you're understanding. Don't forget, you can ask Carla questions. So first I divide. I use long division. And I end up with 2x as my quotient plus -x squared minus 7x minus 12 over our denominator. Okay, we could do this division. I know you can do this division. Review your notes from chapter 2 if you need to. You've got this. Now we can factor the denominator. X cubed plus 4x squared plus 4x. First thing I'm going to do is take out an x. That'll leave me with x squared plus 4x plus 4. And that looks like an x plus 2 all squared. Okay, so here's my form. I have an x, so I'll have a over x. Remember, if this is a single power, this has to be a constant. We haven't got into the other ones yet, the irreducible quadratics. X plus 2 is a factor. It's a factor twice, so I have to write it twice as a first power and then as a second power. If this were a 5, I would have first power, second, third, fourth, and fifth powers, all with a different variable that we're trying to discover over top of them. It's a nightmare. So after we have our form, we multiply by this denominator, wipes it out on the left-hand side, minus x squared minus 7x minus 12. A gets multiplied by x squared plus 4x plus 4. Or actually, I wrote it like this. Good on me. A gets multiplied by the x plus 2 all squared, right? It had the x, not the rest. B has a single x plus 2, so it gets multiplied by x and x plus 2. C already has both x plus 2s, so it only gets multiplied by the x. And this x plus 2 squared, I used this right here, right? We'd already had it written out. So I multiplied a by this. So I have ax squared plus 4ax plus 4a. Multiply here, bx squared plus 2bx plus cx. And I can equate coefficients. Looking at the x squareds, I have a minus 1, an a, and a b. Minus 1 equals a plus b. The x's, I have a minus 7, 4a plus 2b plus c. And the constant terms, a negative 12, I have 4a, fantastic. One of these gives me something I can use. If 4a equals negative 12, a equals negative 3. Knowing a is negative 3, I could put it in my top equation. Negative 1 equals negative 3 plus b. If I add 3 to both sides, I get b equals 2. I know a is negative 3, b is 2. I can find c. Notice no need for elimination, substitution, anything fancy like that. When we get these equate coefficients, a lot of times we'll have just an easy answer. And that's why I wanted to show you this method in as many examples as possible. A is negative 3, b is 2. In this equation, negative 7 equals negative 12 plus 4 plus c. Negative 12 and 4 is negative 8. If you add 8 to both sides, you'll get c equals 1. A is negative 3 over x. B is 2 over x plus 2. C is 1 over x plus 2 squared. And we have our partial fraction decomposition. Fantastic. Yep, we're going to do about 4 more of these. Here we go. Write the partial fraction decomposition of 3x squared plus 4x plus 4 over x cubed plus 4x. A second power in the numerator, a third power in the denominator. Awesome. It's a proper fraction. We don't have to divide. I want to check real quick. Did I? I did not. Look at me. In this answer box, I would absolutely need to include my 2x. Yes, I absolutely need to include that. I forgot this quotient part. And if you only put these fractions in the answer box on WebAssign, you would have been wrong and I would have felt bad about it. But now that I fixed it, we should be good. All right, the 2x, I'd probably put it at the front. It shouldn't matter either way. Okay. Yeah, I thought I messed that one up. I'm so glad I went back. Okay, so we have a proper fraction. Factor our denominator. X cubed plus 4x. They have an x in common. And I'm left with x squared plus 4. We know that x squared plus 4 equals 0 only is solved by complex numbers. So this is what's called an irreducible quadratic. It has no linear factors. So in our form, 3x squared plus 4x plus 4 over x cubed plus 4x, we'll have a linear term with the x. All right, don't want that color. I want the light gray. We'll have a linear term with x, and we'll have a quadratic term with x squared plus 4. Notice linear is power of 1. I can only have a constant above it. But when this is quadratic, a power of 2, I could have a linear term. So we'll use bx plus c. B could be 0, c might end up being 0, but both of them won't end up being 0. Okay, so we have the possibility of a linear function over top of a quadratic, but only a constant when the denominator is linear. Let's multiply both sides by that denominator. We'll have 3x squared plus 4x plus 4 equals a times x squared plus 4, and bx plus c times x. Notice it's like we're cross multiplying. Okay, but we have to keep in mind when there's more than 2, we have to multiply by everything that's missing. Distribute ax squared plus 4a, bx squared plus cx. Yep. So now we can equate coefficients. Let's look at our squareds. 3 on the left, a plus b on the right. 4x on the left. The only thing that has a single x is c, so 4 is equal to c. 4 is a constant term, equals 4a. If 4a equals 4, a equals 1. If c equals 4, well, it's pretty clear that c equals 4. And if a is 1, b has to be 2. So I go back to my form. I know a is 1, so I'll have 1 over x. I know b is 2 and c is 4, so I'll have 2x plus 4 over x squared plus 4. Remember, these 4's do not cancel. Don't go trying to do more. Stop there. It's a quit while you're ahead problem. So even when it's a irreducible quadratic, it doesn't necessarily mean it's a more difficult problem. It just means we have to look for a couple more terms. Let's do it again. It's a proper fraction, so we're good to go. We'll factor that denominator. X cubed plus x, I could take an x out. That's x squared plus 1 remaining. Irreducible quadratic. So we'll have the form a over x, bx plus c over x squared plus 1. Multiply both sides of the equation by this least common denominator over here. A will end up multiplying by x squared plus 1. Bx plus c will be multiplied by x. We can multiply all of this out. Notice that we'll have 1x squared equals ax squared plus bx squared. 1 equals a plus b. 2x equals cx, so 2 equals c. 3 equals a. Look at that. A and c are pretty easy. If a is 3, a b must be a negative 2. So we'll have a 3 over x, a over x, plus bx plus c, negative 2x plus 2 over x squared plus 1. I know I'm cruising through these now, but remember, it's the same process every time. Is it a proper fraction? No, divide. Yes, move on. Factor that denominator so you can write your form. Once you have the form written, you multiply to clear out your denominator. Now you can equate coefficients, solve any systems that come up, and replace your a, b, c, and so on. 2 more examples. Write the partial fraction decomposition of 8x cubed plus 13x over x squared plus 2 squared. Now keep in mind, x squared squared is the 4th power. So this denominator is a 4th power, numerator is a 3rd power, so this is a proper fraction. It happens to also already be factored. X squared plus 2 is irreducible. So we write our form, 8x cubed plus 13x over x squared plus 2 squared. Irreducible quadratic happens twice. So we'll write it once as a 1st power, and then the 2nd time as a 2nd power. Just like when we had repeated linear factors, we had to write the form as many times as it occurred. Right, 2nd power, so we write it twice. Same thing here, irreducible quadratic to the 1st power, irreducible quadratic to the 2nd power, a potentially different linear term up above. Now when we multiply, This is our LCD. So we'll we'll multiply both sides of the equation by x squared plus 2 all squared. On the left, we'll get 8x cubed plus 13x. On the right, ax plus b is missing an x squared plus 2 from its denominator to make the common one. Cx plus d is not missing anything from the denominator. But notice, we can't just have c as 8 and d as 13 because this is not linear. This is not small enough to be over top. All right, let's just go with it. Ax plus b is missing an x squared plus 2. Cx plus d is missing nothing. Distribute. Ax cubed plus 2ax plus bx squared plus 2b plus cx plus d. X cubes, I have 8 on the left and I have a on the right. So I know a is 8. X squareds, I have 0 x squareds on the left, but I'll have a bx squared on the right. So b has to be 0. 13 x's on the left, 2a plus c on the right. 13 equals 2a plus c. 0 is our constant on the left. On the right, however, 2b and d have no variables, so they are also constants. But check it out. If a is 8, 2 times 8 is 16. 16 minus 3 will give us 13, so c is a minus 3. If b is 0, 2 times 0 is 0. 0 plus d is 0. D has to be 0. And my dogs are saying hello. Okay, stop. So we write it all out. We have a is 8, b is 0. So 8x plus 0. No, you do not have to write the plus 0. I just wrote it for emphasis. Over x squared plus 2. C is negative 3. D is 0. Negative 3x plus 0. Again, you don't have to write the 0. I just did it for emphasis. Over x squared plus 2 all squared. All right. Last problem. And I went with the green. That green. X squared plus 2 all squared. Again, same denominator. That's a fourth power on the denominator. So it's a proper fraction. It's already factored. And we'll have the same form as last time. The only thing different is over here in our numerator. X squared plus x plus 2 all over x squared plus 2 squared. X squared plus 2 to the first power. X squared plus 2 to the second power. Since it's an irreducible quadratic, we use a generic linear form on top. Ax plus b, cx plus d. Multiply both sides by this common denominator. It is eliminated for both of these fractions, right? The far left and the far right. In the middle, when I multiply by this, a single x squared plus 2 cancels out. So I'll have ax plus b times x squared plus 2. And when we distribute that, it's much like last time. Ax cubed plus 2ax plus bx squared plus 2b plus the cx plus d. Equate coefficients. I see an x to the third here. There's no x to the third here, so I count that as 0. We have to equate all the coefficients. Don't just look over here. Look at both sides. Which one's the largest and start there. So a is 0. 1x squared equals b, so 1 equals b. Here's an x, there's one of them, equals 2a plus c. And the constant term is 2. Constant term is 2b plus d. All right. In this instance, a is 0. If a is 0, c must be 1. If b is 1, b is 1. 1 times 2 is 2. 2 equals 2 plus d. D must be 0. So I find that if a is 0 and b is 1, I'll have 0x plus 1 over x squared plus 2. Notice I didn't write the 0x this time. C is 1, D is 0, so that's 1x plus 0. Again, I didn't write the 0, just x over x squared plus 2 all squared. This is the most random section to be put in Chapter 7. You're going to see it again extensively in Cal 2. You'll see it a little bit at the end of Cal 1. But overall, It's just my favorite section because it's so weird, but it's so useful. I like to be able to break down fractions into smaller parts. I don't know why. It has it been helpful in my life? No, not really. Like, never been anywhere like sitting at the beach or something, like Wet and Wild, chilling. Partial fraction decompositions never come up. But I still love it, and I hope you're doing all right following these lectures. I've really got to go ice my leg right now. It's been down for a couple of hours, and it's hurting. Might take a little pain med. Thank you for your continued patience. I'm not going to let you down. I'm going to make sure you're fully prepared for exam 2. I will be there all 3 days next week, including for my office hours, although I'm probably going to change locations for that. What else? I'm going to catch up on email today. So if you've asked for anything in the last week, sorry. Really sorry. I'm a little late. I'm getting to it. Thank you.